There is nothing in this class that should require a calculator. We were in the sand, you know, Archimedes doing his circles in the sand. Do you guys know these stories? You know who Archimedes is? Have you heard of Archimedes? Okay. So he like, anyway, I'm not going to tell you this story. It'll take too long. But there's a great, look up Archimedes, you know, don't touch my circles. He's working, I'm telling you the story. As I said, I wouldn't tell you the story. Good. Okay, sorry. Keep it like this. Anything else before we go? Going once, going twice. Let's do it. All right, pre-calculus review. Let's see. I think I can do this. Let's try this. Okay, pre-calculus review. All right. One of the most important things that you have to understand before we do calculus is, again, we talked about this a little bit last time, the use of our visual cortex. And the Greeks, the ancient Greeks, the Greeks understood and had a lot of technology, a lot of great insights into two things: geometry, things like circles, lines, parabolas, you know, all of that stuff is ancient Greek stuff. They also understood algebra. They wouldn't have called it algebra. Is algebra. It's Arabic. Comes from an Arabic treatise of what is now called algebra, but it transferred from Persia to and elements from India. I mean, this is from math is a universal thing that everybody's involved in. So algebra, things like you know, y squared plus x cubed minus 7x equals whatever, right? I'm just writing down an algebraic equation, a polynomial equation in some variables. Of course, that's a modern version of it, but they understood something about algebra, they understood something about geometry, but never the two should meet, in the sense that there was no relationship between things like, if I write x squared plus y squared equals 1, probably most of you have a mental image of what that is. What is it? It's a circle, okay? This was not in any way understood to the ancient Greeks. It's not until, does anybody know why you think of x squared plus y squared equals 1 as a circle? There's something called the Pythagorean theorem is very important in this, absolutely. The reason this is a circle is the Pythagorean theorem. Conics, okay, all of these things are conic sections, that's true. The way to, I'm getting at the notion of a graph. So the notion of a graph, when would you, the reason you think of this as a circle is you're thinking of the graph. The graph is a set of all pairs, x and y, in a plane, and the plane is called the Cartesian plane, which is called that because of René Descartes. So Descartes, okay, from which you get the Cartesian plane. He's the guy, this is like 1630s. He's the reason these things are connected, that you can graph. The idea of a graph comes from René Descartes, who said, anytime you have some algebraic relationship, you can realize that algebraic relationship as a graph. And so what is a graph? You take, so for example, what does it mean to graph? Let's graph. I don't have to write these on it. Let's graph. And I'm working on my handwriting. It's a work in progress. So if you can't read something I write, please tell me and I'll try to write it better. If we try to graph x squared plus y squared equals 1, that means we're going to take we're going to draw the Cartesian plane with x here and y here. And we're going to plot all pairs x in the horizontal direction, y in the vertical direction, satisfying this equation such that this holds. Okay, and by the Pythagorean theorem, that graph will be a circle of the unit circle of radius 1. Okay, so far so good. Is this a function? What's the difference between functions and graphs? It's not a function because exactly. Everybody's saying the same thing. So what is a function? We can't have, the best way to define a function is what it isn't. Can't have f of 2 equals 3 and f of 2 equals 7. You give me an input, I got to give you an output, but it's got to be one output. It can't be multiple outputs. Okay, so this fails the vertical line test, right? There are two possible values on this graph for a given value of x. So it's not the graph of a function. This is not a function. But there are two functions being graphed at the same time. The two, if you want to solve for y equals, you can, the most common thing is to graph not just some graph, but the graph of a function. So if we have a function f of x, we can graph y equals f of x. That's the algebraic relation. Means for every value of x, you work out what f of x is, and that's the pair x comma y that you place. All right. And so what are those functions? In this case, x squared plus y squared equals 1. How could we make that into a function? Let's solve for y. Yeah, square root of 1 minus x squared. So that's the top half. And then there's the same thing with a minus sign with the bottom half. So far, so good. Any questions? We're going quickly over this stuff because this is all hopefully review, and we're just connecting, removing cobwebs. Removing cobwebs. Okay. What's the domain of this function? Yeah, so by domain, we mean what values of x are we allowed to plug in and get a meaningful value for the function. Sometimes a domain is specified. So when I say domain without, I could say, I just want the domain to be from 0 to 1. And then you would just graph this much of the function, right? So if I'm saying, what's the domain? I mean, the largest possible domain. Yes? Yes, exactly. The domain is minus 1 to 1. Those are the values. Y is at minus 1 to 1. Say it again. It is the unit circle, but if we didn't know that, how could we figure out that the domain is minus 1 to 1? Exactly. Where do we have problems with square roots? On negative values. So we need, how do we know that the domain is y is the domain minus 1 to 1? We need 1 minus x squared to be non-negative because we're taking a square root. Right? Ring bells? Okay. And if I move the x squared to the other side, that's the same thing as 1 being at least x squared, which is the same thing if I take square roots of both sides as 1 being at least x. Say it again. Plus or minus. So how does plus or minus work with inequalities? The sign changes. So 1 needs to be at least x, or actually, if in this case it's and. The two possible solutions, so people get confused about this. If you have, how can x squared be less than 1? There's a variety of ways of thinking about this. One way is to think about the graph of y equals x squared. What will the graph of y equals x squared be? A parabola. And then I want to know, when is that parabola below 1? Well, here's the value y equals 1. And here's the region, or here rather, is the region where x is less than 1, where y is less than 1, which is when x is between minus 1 and 1. Or when you have these square roots, you need this to be true, and you need negative 1 to be greater than x, which is the same thing as x is, to be less than or equal to x, because the minus signs flip. So that's the range. So that's where we get this domain minus 1 to 1. Okay. So if I gave you some weird square root thing, how would you figure out what the domain is? Tell me your name. Yusuf. Exactly. You take the inside and you make sure that you're never taking square roots of negatives. How would you figure out the domain if I'm dividing by something? What can't you do when you're dividing? Denominator is not 0. Okay, great. And so that's the domain. What's the range of this function? So let's go back to this function y equals square root of 1 minus x squared. What's the range? It would be negative 1 to 1. So what does range mean? It's the set of all possible values that the function takes. Tell me your name again. One more time. Raga? Everything greater than or equal to 0? So in other words, 0 out to infinity? Up to 1. Yeah, tell me your name. Ethan. You were going to say the same thing, right? So you go from 0 is the smallest value that y attains, and 1 is the largest value that y attains. Okay, if we just are tracking the y variable, the y values of this function just go from 0 to 1. Okay, so the range is not from 0 to infinity. It is 0 to 1. And the square brackets, these are supposed to be square brackets. Square brackets means including the endpoints. If I didn't want to include the endpoint, I would write parentheses. Okay, good. Good. What else? How about, what do we know about lines? Lines. Can somebody give me the equation of a line? Any equation? Tell me again. Dan. Okay, that's a general line. Yep, give me a specific line. Okay, great. Y equals 3x plus 2. Now you gave it to me in a very particular form. What is this form called? In general, it would be y equals mx plus b, which kind of is suggesting what these things are. Tell me again. Lakshmi. Right, so this is slope-intercept form. Slope-intercept. And what does that mean? Tell me your name. Drew? Yeah, M is the slope and B is the y-intercept. Exactly. So M is the slope and B is the 3 is the slope. This is the y-intercept. Exactly. So if we wanted to draw this, we already know basically all the information we need. The y-intercept is 2. In other words, when I said x equal to 0, this is the y-intercept, i.e., if I set x equal to 0, that tells me the value of y. Right? If I set x equal to 0 here, the value of y will be b. So the value of y will be 2 in this case. So that's 0, 2. That's our y-intercept. That's where we start. And then we go at a slope of 3. Every time I take 1 step over, I have to take 3 steps up. That's it. That's allowed. Okay? This is boring. This is review. You should be bored. We're going to go quickly, but you should be bored. What's another version? What's another line form? Tell me your name. Anna. Beautiful. That's another form. Ax plus by equals c. Yep. How would you give me Anna? Give me some random numbers for a, b, and c.
2x plus 6y
equals 8. Beautiful. Let's try to graph this. Okay. Take a second and graph it. And give me a thumbs up when you're done. Okay, a couple of thumbs up. So how'd you do it? What's a really easy way? Tell me again. Sid. You can convert it to slope-intercept form. You absolutely can do that. Yep, you can move between these forms interchangeably. Is there a lazier way to do it? Tell me again. Nimmer. You can find the intercepts. Yeah, so what does it mean to find the intercepts? Yeah, just plug in 0. Plug in 0 for x. So if x equals 0, if x is 0, if there's no x here, then y has to be 8/6, same as 4/3. Okay, so that's if x is 0, y is 4/3, 1 1/3. If y is 0, x is, if there's no y, x is 4. That's it. I have 2 points, 0, 1, 2, 3, 4, and now I draw a line through 2 points. Done. Okay. Is there another form of a line that you guys know of? Tell me your name. By?
I don't know, but it's where you place
Point slope form. Yeah, point slope form. Let's see. I have a little room here. Let's add point slope form. Point slope form. Point slope form looks like, can you give me a sample?
So like y minus x1 equals m parentheses x minus x. Y minus y1.
Yep, that's better. Okay, give me an example.
Y minus 3 equals 2 x minus 2.
Okay, so this is called point slope form because it immediately allows you to read off two things. What are those two things? Tell me your name. Arush. A point and a slope. Yeah, what's the point that we can read off? Yeah, let's make both sides 0. 0 is the name of the game. Make things 0 and your life will be easy. 0 is a very easy number to work with, unless you're dividing. So if I want to make this side 0, I make x equal to 4. If I want to make that side 0, I make y equal to 3. So that's 4 comma 3, 1, 2, 3, 4, 1, 2, 3. All right, there's my point, and the slope I read right off of here is 2. So if I go over 1, I go up 2. There's my line. Okay, so far so good. All right, we remember about circles. What do we know about circles? Can somebody give me a random equation of a circle? Any questions so far? Am I going too fast? No, I'll review. Good. Random equation of a circle. Other than Dan? Tell me your name. Andrew.
X plus 3 squared.
Okay.
Plus y minus 2 squared.
Equals 4. Great. So that's a great equation of a circle because it automatically immediately tells you where it's centered and what its radius is. Where is it centered? Negative 3, 2. 1, 2, 3, 1, 2. There's the center. What's the radius? 2, because that's 2 times 2. Okay, so if I go over 2, there's my circle. Done. What if I gave you something a little harder? How about x squared plus 2x plus y squared minus 4y equals 7? I don't know. I just made something up. Bless you. Why is that the equation of a circle? Tell me your name. Anna. Anna. Yes, let's complete the square. Okay. You want to work on this for a minute? Want to try it yourself? Work on this for a minute. Figure out where the center and what the radius is of this. Sorry, I have to hold still. You guys can see this okay? In the back, in the front? Okay. Leo? Will, it's okay? You can see it? All right. Thumbs up when you got it. All right, a whole bunch of people have got it. How do you complete a square? Tell me your name. Akil. Right. It's literally completing a square is literally, let's look at this. If I have an x by x square, and I want to add 2x to it, let's complete this square. Well, adding 2x is adding a 1 by x here, and a 1 by x there. So I'm missing a little bit. What am I missing? 1. I'm missing a 1 by 1 square. So I'll add 1 and I'll subtract 1 because I'm not allowed to change it. So I add 1 and subtract 1. Right? That's what completing the square is. It's literally, that's why it's called that. Okay, so this part becomes x plus 1 by x plus 1. Right, x plus 1 squared. Okay, how about this? What am I going to do with this? Add a 4, because that's the square of half of 4. So I add 4 and I subtract 4. So I have x plus 1 squared plus y minus 2 squared. Here there's a minus 1 left over. Here there's a minus 4 left over. So that together is minus 5. When I move to the other side to join the 7, I get 12. And so this circle, let's try to separate these. This circle is centered at -1, 2, -1, 2, with radius square root of 12. I made it up, so it's not surprising that we got a random number there. Radius root 12. The radius is root 12. So far, so good. Good. We know about lines, we know about circles, we know about domains and ranges. We know about parabolas. What's this parabola? X equals y squared. Right. It's not a function. That's okay. We can still graph an algebraic relation. The graph is x is always positive, y can be positive or negative, and it's a parabola on its side. Okay. Good. Very good. Let's talk about symmetry. So some functions have symmetry. Let's talk about symmetry. So what does it mean? So I'm going to graph a little bit. What does it mean for this to have even symmetry? Tell me again. Yusuf.
Over the x-axis.
It's mirror symmetry over the other one, the y-axis. Mirror even means mirror across the y-axis. Okay, so how would I continue this function? What does this function have to look like for it to have even symmetry? Take a second and try to draw it. Sid, you were about to say? Draw it for yourself before I draw it. Oops. Okay, thumbs up. Anybody? Couple thumbs up. Let's do it. How would I draw the mirror symmetry across the y-axis? Yeah, I just mirror it. I just do the best I can. Up a little bit and then down and then over and whatever. Okay, there it is. Right? To make it even, what does it mean to make it even? If I look at a value like -x, if I go out a distance -x and I want to know what the value of the function is at -x, what should I do? I go out to the same thing at +x and go up the same height. Okay, so an even function is one which has symmetry across the y-axis in a mirror. Good. What's the odd symmetry? That's a good guess. You would think mirror across the y-axis. If I mirror this across the x-axis, rather, I would get this. This is hard to draw. I would get this, but that's not a function. Doesn't pass the vertical line test. Tell me your name. Fatima. That's also a good guess. That is how you get the inverse function. We're going to talk about inverse functions in a second. Tell me your name. Shelley? Shirley. The odd symmetry. Origin symmetry? Yes, exactly. So this is rotational symmetry about the origin. So 180 degrees, 180 degree rotation on the origin. Okay, so if I have some random looking function, whatever it's doing, what I want to do is turn my head upside down 180 degrees and draw what I would see. So if I'm going up, I need to go down, and then this is going to do that. And then there's a big swing to the bottom. And then there's like this kind of thing, and then it trails up. Okay. So that's 180 degrees if I rotate things 180 degrees from one side to the other, from the first quadrant to the fourth quadrant, from the second quadrant to the third. Okay, so what does that mean at the level of the function? If I go out a distance x, negative x, so f of negative x, what's the value that it should take? If I go out a distance positive x, that's the value of the original function. If I go in the negative direction, I negate the value that I saw in the positive direction. Okay, so this is odd symmetry, this is even symmetry. Every function is even or odd, right? No, most functions are neither even nor odd. What's a function that's both even and odd? Other than Sid? Tell me your name. Laban? Devon? I'm deaf, I'm sorry. Spell it. N-A-B-A, Naba. Y equals 0 is the only function that is both even and odd. Why? So even and odd implies f of x equals 0. In other words, y equals 0. Y equals 0, think about the graph of y equals 0. Here's the graph of y equals 0. If I rotate it 180 degrees, yeah, it's symmetric. If I reflect it across the y-axis, yep, it's symmetric. It has to be, the values at negative x have to both be equal to the values at positive x and the negative of the values of positive x. But the only thing that agrees with its negative is 0. Okay? Most functions are neither even or odd, but you should know about these important symmetries. Okay. Any questions on symmetry? Any questions on lines or circles? Okay, let's review a little bit of trig. Trig review. All right. What is trigonometry about? It's about triangles because triangles is in the name. It's kind of funny, by the way. Triangle talks about the fact that there's 3 angles in a triangle. Trigonometry is studying about trigon. What's a gon? What's a 4-gon or a 5-gon? A pentagon. Gon means what? A polygon, yeah, but gon.
Corner angle.
I think gon means side, like a quadrilateral is something with 4 lateral, like your lat is 4 sides. So it's just funny how we talk about triangles, but quadrilaterals. Triangles have 3 angles. They also have 3 sides. Quadrilaterals have 4 sides. They also have 4 angles. But anyway, never mind. So trigonometry is in its name says it's about triangles, but it's actually about circles. Trigonometry is really the study of circles, and it's the study of that first equation that we have, x squared plus y squared equals 1, and the Pythagorean theorem. So if I just write x squared plus y squared equals 1, you all know that it's that the solutions to this equation are form a circle when you graph it in the Cartesian plane, thanks to ideas developed by followers of René Descartes. But how do we actually parametrize the values? Is there one function or pair of functions that will tell us what every solution to this equation looks like? How do we solve this equation, x squared plus y squared equals 1? Say it again. Well, it's trigonometry, so what functions am I looking for? Sines and cosines, exactly. So if I set x equal to cosine theta and y equal to sine theta for an auxiliary parameter theta, as the value of theta ranges, we get all solutions to this equation. So this is a parametrization of the circle x squared plus y squared equals 1. In particular, we have the equation cosine squared plus sine squared equals 1. And so if I have a triangle, if I have a point on the circle, thanks to the Pythagorean theorem, can be realized in terms of a right triangle. I mean, that's how we set up this Cartesian system, is to have right angles between the x coordinate and the y coordinate. This length we already said was going to be 1. What's this? So let's call this angle theta. Theta is the distance we've traveled. Theta is the angle, but theta is also the distance that we've traveled. In what measure of distance? Tell me your name again. Raga. In radians. So this is distance in radians. Theta, well, if this one is 1 foot, let's say this is 1 foot, whatever the units are, let's say that's 1 foot. Then if you actually walk along this circle, this will be theta feet. That's the beauty of radians. Radians tell you what the actual distance is along that arc, as opposed to degrees. Degrees, how do you convert from degrees to radians? Yeah, you just have to remember that there's 360 degrees all the way around. There's also how many radians all the way around? Why is it 2 pi? Right, each of these, yeah, so I mean, it's practically by definition. Pi is the ratio of the circumference to the diameter. This 3.14 is the ratio of circumference to diameter, and our diameter is 2, because our radius is 1. So all you have to do is convert from 360 degrees to 2 pi radians. This is all review. Everybody's bored, right? I don't want you to be completely bored, but I realize this is review. Okay, I'm going to stop apologizing for the fact that this is review. Let's go. What's this distance? It's the x coordinate. Yeah, it's cosine. That's the whole point of setting x equals cosine, because that's how far we go in the x direction to get to this point. This point, x comma y, has x equal to cosine theta, which is adjacent over hypotenuse, the adjacent to the angle over the hypotenuse. The hypotenuse is 1. And this distance, sine, because we made y equal to sine of theta. Okay. There's for any point like this, there's a tangent line to the circle. Anybody know what this distance is? A tangent line means that this is a right angle. So now we have another right triangle from here to here to here. What's this distance?
1.
This distance is 1. You're telling me this triangle has to be equilateral? So relative to this angle theta, it is the opposite over adjacent. Sine over cosine is tan. That's why it's called tan. It's the distance along the tangent. This is the tan, which is sine over cosine. Opposite over adjacent. Okay. What about this distance? Anybody know what this distance is? The cotan, exactly, cotan. Why? Well, if this angle is the complementary angle to theta, then this angle is also theta. And now I have a 1 here, and then this distance, and a right triangle. So this distance, relative to this angle, is adjacent over opposite, which is cotan, cosine over sine. And if you think about it, what happens as this angle, what happens as this point goes down to 0? What's the distance tan? What happens to this part of the tangent line as this point goes down? The tangent line gets closer and closer to just a dot, so the tangent goes to 0. But what happens to the cotan as I come down? As this point comes down, cotan gets longer and longer. Cotan's blowing up. Okay. What about, you know what this distance is called? Let's get another color. You know what this distance is called? This line that cuts through the circle is not tangent to the circle. You know what it's called when you cut through something instead of being tangent to it? Secant, yeah. So this is the secant. Secant of theta, this distance from here to here. And what is that? Yeah, in terms of this angle, it's hypotenuse over adjacent. Adjacent is 1. So it's hypotenuse over adjacent, that's 1 over cosine. And how about this distance? From here to here. Cosecant. Okay, so trigonometry is about, yes, it's about triangles, but it's really about understanding the geometry of the circle. Tangent lines to the circle, secant lines through the circle, and those distances, and the cosine and the cosine, tangent and the cotangent, all of these things are sitting right there in the circle of the triangle. Okay. Good. We have this equation. That means we can get two others. If I divide both sides by cosine squared, if I take the Pythagorean theorem, cosine squared plus sine squared equals 1, let me divide both sides by cosine squared. So what's cosine squared divided by cosine squared? 1. What's sine squared divided by cosine squared? Tan squared. What's 1 divided by cosine squared? Secant squared. Beautiful. What if I divide both sides by sine squared? Cosine over sine. One more time, cosine over sine. Cosecant, sorry, I didn't finish writing here. Cosecant, what is cosecant in terms of sine? 1 over sine, exactly. So cosine over sine is cotangent. Sine squared over sine squared, 1. And 1 over sine squared, cosecant squared. Okay, beautiful. What else do we know about trigonometry? We know the cosine law. If I have an arbitrary triangle, let's say I have a triangle with angles A, B, C, and corresponding sides A, B, C. What's the cosine law? Yeah, it's exactly. Who's somebody saying it? Tell me again. Nimmer. So it's the Pythagorean theorem with the modification. Yeah. So a squared plus b squared is equal to c squared. That's the Pythagorean theorem. And then there's the adjustment minus 2ab cosine of the angle c. Okay, if the angle c is equal to pi over 2, what's cosine of pi over 2? Oh, we didn't graph the sine and cosine functions. Let's do that in a second. What's cosine of pi over 2? 0. Cosine of pi over 2 is 0, so this disappears and we get the Pythagorean theorem. So this is a generalization of the Pythagorean theorem. Tell me your name. Janini? Janini. What does that say? This? Yes, let's fix that. Thank you. Try again, but this time in English. Cosine law. Thank you for helping all the other people who were similarly confused. This doesn't look so good either. Cosine. And that's a B. All right, if I actually try to write A times B times cosine is. Okay, cosine law. What else? Yeah, let's graph these things. We haven't graphed them. So what is the graph? What happens to the sine as you go around the circle? What the sine is the y coordinate, right? So you start at 0, you go up to 1, you go back down to 1, and you come back and you sort of are oscillating up and down. So over time, if you think of theta as time, and this being the motion around the circle, for some ungodly reason, clocks start here and go this way, and in math, you start here and go that way. Sorry, history. Too late to change it now. So what is the graph of sine? If I say y equals sine theta, what is the graph of that in the theta y plane? Yeah, everybody's doing the squiggle. Right, so we start at 0. We make our way up to 1. By the time we get to a quarter of the circle, by the time we get to pi over 2, all the way around is 2 pi. So a quarter of that is pi over 2. By the time we get to pi over 2, we get to 1. When we get to pi, that's when we're back to 0. And when we get to 3 pi over 2, we jump down to -1, which I didn't make room for. And then at 2 pi, we're back to 0. Okay, so the graph looks like this. And it keeps going. Is this function odd or even, or neither, or both? Okay, it's not both. It's odd. It's odd because when we take it and we flip it around 180 degrees, Okay, so this is odd. This is an odd function. Good. How about cosine? What does cosine look like? 0. Whoops, I don't want a dot there. I just want a 0 there. Pi over 2, pi, 3 pi over 2, 2 pi, and so on. So the x coordinate starts where? 1. The x coordinate starts all the way out here at 1. It goes down to 0 as theta moves to pi over 2. And then it goes all the way to -1 before coming back up. Okay, so the x coordinate is going back and forth on the circle. And that's, let's see, will I confuse you if I say x equals cosine of theta and this is the x direction? Let's not do that. Let's call it y equals sine theta. This is sine, this is y, even though before, okay, we're changing our dummy variables. So at 0, we get 1, at pi over 2, we get 0, at pi, we get -1, and this is the graph of cosine. Okay, is why did I write sine? No one was going to say anything? You were waiting for me to shut up to patiently say this is cosine. Is the cosine function even, odd? Does that have any symmetry? Even. This function is even. So the points on opposite side of the mirror across the y-axis agree. So far, so good. Okay. Very good. That's sine and cosine. Let's graph the other ones. So what do you want to graph next? Tan. Let's graph tan. Y equals tan theta. So I know that the special points will be pi over 2, pi, 3 pi over 2, and 2 pi. Before that, what's the amplitude of the sine and cosine function? You know what amplitude is? It's amplitude is how high you oscillate. So this is amplitude. Amplitude. Okay, you're oscillating from the center, you're oscillating +1, -1, +1, -1. So the amplitude is 1. And what's the period or wavelength? The period is 2 pi. Oops, I overshot a little. Okay, so this is the period. Now, these graphs actually look pretty similar. Is there any relation between them? Yeah, if you shift one over a little bit. So how do we shift the graph? Yeah, if we change the x minus something, we'll change the graph by moving it by whatever that amount is. So if I take cosine of x minus what? If I want to get sine. Yeah, let's see if that's right. I think that's right. So when x is 0, I'm supposed to get 0 on this side. If I put in 0 for x here, I get minus pi over 2, and cosine at minus pi over 2 is indeed 0. So if I take the cosine graph and I shift it over by pi over 2, I get exactly the sine graph. Okay, and of course this is meant to turn around, not keep going up. Tell me again. Raga. If we did x plus pi on 2, if we did so here's a good exercise. Cosine of x plus pi over 2. Express that in terms of sine of something. Is that a hand? No, that's a stretch. Tell me again. Rohin. X plus pi?
Oh, sorry, x minus. Yeah.
Minus? In fact, with pi, it doesn't matter if you add or subtract because the period is 2 pi. So let's see if that's right. So let's stick in what's a nice value to stick in? What's my favorite value? 0. Okay, let's stick in 0. Sine of negative pi, when x is 0, I want sine of negative pi. Negative pi is over here, and that's at height 1. Sine of negative pi is the same as sine of, I'm sorry, this graph is not to scale. there's negative pi. That's there's negative pi. There's negative pi over 2. There's 3 pi over 2, and negative, of course, and negative 2 pi. Okay, let's try that again. Sine of negative pi is 0, same as sine of pi being 0. And then cosine of pi over 2 is also 0. Now, what happens as I move a little bit forward from this point in the graph? As I move a little bit forward from this point in the graph, I start going negative. And what happens if I move a little bit from this point in the graph? I start going negative. Okay, so yes, these agree. Everybody see that? You're gonna have a lot of problems on the homework to remind you how shifting. What if I wanted to shift it up or down instead of shifting horizontally? You just add something, right? If I take sine of x plus 7, then it's going to go from 7 up to 8, down to 6, up to 8, and so on. Okay, so shifting vertically is kind of obvious. Shifting horizontally, you have to think for a second. Are you pushing to the left or to the right? Good. What about if I want to make something bigger? Scale. How would I make the amplitude 2? Tell me your name. I'm sorry. Don't tell me your name. Jenny. Yes. Yeah. Exactly. 2 sine theta oscillates not between -1 and 1, but between -2 and 2. Right? Okay. This is all review. I realize. How many of you are bored? Okay, a couple of you. It's useful review, hopefully, for many of you. Where were we? We were about to graph tan. Let's graph tan. So tan is sine over cos. Sine over cos. That's a useful way to think about it when you're graphing it. So let's look at these two graphs and try to figure out what the quotient of one by the other would be. Whenever the numerator is 0, we're going to get 0. Whenever the denominator is 0, we're going to get undefined. We're going to get an asymptote. Asymptote. Okay, so where is the numerator 0? At 0, at pi, at 2 pi. So we're going to pass through 0. Where is the denominator 0? Where is the denominator 0? Yeah, at pi over 2. So that's going to be an asymptote. 3 pi over 2 is going to be an asymptote. As I move and negative, let's go to negative pi over 2. That's going to be an asymptote. As I move a little bit forward in y, I get a positive value. And here I also get a positive value going out to 0 in the denominator. So tan is going to look like it's going to be positive until it blows up. And how about if I move backwards? The sine is negative, but the cosine is still positive. So negative over positive, negative, right? Okay. And then it's periodic. In fact, with period pi, not 2 pi, its smallest period is pi, because these two, well, yeah, the two periods sort of not cancel out, but they shorten as a result of taking the quotient. Okay, so far so good. How about the graph of secant? Let's graph secant. Okay, let's graph secant. Y equals secant theta. So secant is, in terms of sines and coses, 1 over cos, 1 over cos. So again, we're going to have asymptotes when cos is 0. Here's 0, pi over 2, pi, 3 pi over 2, 2 pi, pi, 3 pi over 2, pi over 2, negative pi over 2. So at all of the pi over 2s and 3 pi over 2s and 5 pi over 2 and so on, we're going to have asymptotes. And if the value of cosine is 1 at 1, what's the value of 1 over cosine? Also 1. Okay. The function cosine is even. There's a symmetry left to right. So when you take 1 over left to right, will you still have an even symmetry? Yes. Right? Yeah, if I take 1 over on this side versus on that side, I still get the same thing. So it's going to be an even function. And I'm going to be blowing up as I move to either pi over 2 or negative pi over 2. I'll be blowing up to infinity. So secant, sorry, yeah. So secant looks like this. Now, what about at pi? What's the value at pi? Of cosine. -1. So 1 over -1 is still -1, and I do this kind of thing. Okay, so that's the graph. Secant, cosecant is 1 over sine, so it's the same graph, just pushed over. Should we graph it, or you'll do it at home? How many people want to graph cosecant together? Okay, enough people said yes, let's do it. Y equals cosecant theta. Okay, so this is cosecant is 1 over sine. Sine has zeros at 0, pi, and 2 pi. So 0, -pi, pi, and 2 pi will all be asymptotes. Where is sine equal to 1? At pi over 2. So at pi over 2, 1 over sine will also be 1. And how about at 3 pi over 2? -1. And then we do the same thing. Okay. So that's the graph of cosecant. Same as secant, just shift it over. Can you guys see? Okay. There's only one more, which is cotan, which is tan shifted. I think we can move on. Yeah. Okay. Good. Other things we need to do. How about the double angle formula or angle sum formulas? What do we know about? Let's start with sine. What do we know about sine of a plus b? Tell me again. Zane.
It's sine A and cosine B plus sine B and cosine A.
Good. How about cosine of a plus b? Anybody remember these? Other than raga. Other than raga. And tell me again. Oh no, don't tell me. Fatima. Go ahead. Very good. This is something I always have to remind myself of, that this is the sum angle formula. The sum angle formula for sine is nice. It's a plus and sort of has the symmetries. Got sine and cosine. The cosangle formula's got a minus when you're adding. So when you're subtracting, what's cosine of a minus b? Let me try to write a little cleaner. What do you get? How many people know the answer? Okay. I guess I'll go a little more slowly. So you learned these things, you just forgot them. It's been a while. Okay. So it's the same thing. You're just replacing everywhere you see a b, you're replacing by a negative b. So what happens in cosine? We replace b by negative b. Is cosine odd or even? Less. Cosine's even. So when we replace b by negative b, nothing happens. But sine is odd. So when I replace b here by negative b, this sign will flip signs. The sign will that'll be a plus. Okay. So it's cosine a times the same cosine of b plus, because this sign is going to flip, sine a times sine b. Okay. I don't have time to derive this for you. Hopefully you either remember or look it up, or will, I hate to not give you everything from first principles, but we have to move. We got a lot of stuff to do. So let's say you understand and have internalized these sum angle formulas, what does that give us in terms of, let's say, double angle formulas? What's sine of 2a? Tell me again. Julius. 2 sine. Exactly, because we get a sine. If I set a equal to b, then here I get 2a. So I just use this formula. Sine a cos a plus sine a cos a. Well, that's just twice sine a cos a. So if you see sine a cos a somewhere, what is your spidey sense starting to tell you? It should be sine of 2a, right? Let's convert it to sine of 2a and be careful, there's a 2 floating around somewhere. There's a 2 floating around somewhere. What about cosine of 2a? So again, I'll use the sum angle formula for cosine. So if a and b are the same, here I get cos a, which is cos squared a, minus sine a, which is sine squared. Okay, so I get cos squared a minus sine squared a. Does anybody know their half angle formulas? Sine and cosine of a half? I don't remember them. You do remember them? Good. Okay, you'll tell us what they are in a second. How could you derive them from what we have so far? Any ideas? Tell me again. Yeah. Nimmer. We have a relationship of a to 2a here. So if we could invert that relationship, we'd have a half angle formula. The problem is here we have both cosines and sines. If only there was some way to convert sines into cosines or cosines into sines. If only there was some magical relationship between sines and cosines that would allow us to convert between them. Right? So what do we want to do with this double angle formula for cosine? One more time. Julius. Julius or Julian? Julius. Beautiful. Yeah, let me put the formula here. So we have cosine squared plus sine squared is equal to 1. So I could, if I move the cosine to the other side, I get the sine squared is equal to 1 minus cosine squared. Or I could move the cosine of the sine to the other side. I get cosine squared is equal to 1 minus sine squared. So what should we let's make cosine into 1 minus sine. So cosine is 1 minus sine squared. And then I have this leftover sine squared. Well, that gives me 1 minus 2 sine squared. Right? But now I can solve for sine in terms of cosine of 2a. So sine of a, or let's say sine squared of a, is equal to what? If I move this to the other side and I move the cosine to the other side, I get 1 minus cosine of 2a over 2. Did everybody get that algebra? And so now now I can replace a by a over 2. That tells me that sine of a over 2 is, well, you have to be a little careful with the square root. Maybe this is just the better formula to leave it in, but it's either plus or minus depending on which value of a it is. You have to be careful in the range in which you're using this, but you'll get 1 minus cosine of a over 2. Bless you. So that's a half angle formula for sine. Take 1 minute and do the same thing for cosine. In other words, what are you going to do to get the cosine half angle formula? Let's just leave it as a cosine squared of a over 2. Cosine squared of a over 2. Take 1 minute and try to figure out what it must be. We're going to take this sine, convert it into cosine, solve for cosine squared, and then replace a by a over 2. Does everybody understand what the task is? Anybody want to review what we're trying to do? No, everybody's hard at work. Okay, go. Give me a thumbs up when you have the half angle formula for cosine. Got it. There. Great. Great. Thank you. You need a little more time? Still working? How many are still working? Okay, take your time. No rush. So, yeah, you could, depending on if you want to write it as plus or minus square root or leave it as a square. So you don't have to work out which one it is. The half angle formula only gives you partial information. You then have to use the value of a/2 to figure out whether sine should be positive or negative in that range, whatever the range is. It only tells you information about the square of the half angle. Okay, looks like people are mostly happy with that. So let's see. If I put in sine, if I replace sine here by 1 minus cosine, well, minus that is cosine minus 1. So I get that cosine of 2a is 2 cosine squared minus 1. So if I move the 1 to the other side, I guess I just get cosine of 2a plus 1. And then I want to divide by 2, and then I'll replace a by a over 2. So is that what you guys got? Cosine a plus 1 over 2. So they're almost the same formula, except one is with a plus sign and one is with a minus sign. And then, of course, again, you would take the square roots and you'd have to work out which square root it is based on the actual input, the location of the input. Okay. Other questions about sines, cosines, double angles, half angles? Oh, a couple more. Let me pause for questions. Yes, tell me your name. Caitlin.
So cosine 2a, the equation underneath it, that's for sine.
So from here to here,
No, on the left.
from on the left, from
Yeah. The bottom equation.
this bottom equation.
Yeah, that's still. Or
So what I did here is I replaced cosine by 1 minus sine.
yeah.
So that is what allowed me to isolate sine by itself. See, the problem with the double angle formula, to go from a double angle formula to a half angle formula, here I have both sine and cosine. And I want to get either one or the other. And there's two ways of doing it. You could replace sine by 1 minus cosine, or you could replace cosine by 1 minus sine.
Yeah.
And depending on which one you do, you'll get a different half angle formula, one for sine, one for cosine. Did I answer your question?
Yeah.
Other questions? Okay, some values of sine and cosine we should be familiar with. So for example, there's two triangles basically in trigonometry. Looks like there's a lot more, but there's only two. There's the 30, 60, 90 triangle. Well, let me just, yeah, whatever. What is this? This must be 30. This is 90. Whoops, this must be 30. This is 60. There's our 30, 60, 90 triangle. That's one we got to know. What is the, how do you guys think about your 30, 60, 90 triangles? What is it? The smallest length is X. Oh, yeah. Let's make X equal to 1 or a half or something. Let's say the hypotenuse is 1. Some people like to make the hypotenuse 2. Let's say the hypotenuse is 1. Then what? How long is X? Half. And how long is Y? root 3 over 2 by the Pythagorean theorem again. Right? Good. So what do we know about sine of pi over what's 60 and 30? 60 is pi over 60 degrees is pi over 3 radians, and 30 degrees is pi over 6, and 90 degrees is pi over 2. Okay, so sine of pi over 3. So we have a couple of on our sine curve, which I drew kind of diagrammatically. At pi over 2, we know we get to 1, but where do we get what's the value of sine at pi over 3? I heard someone say something. If our angle is pi over 3, sine is opposite over hypotenuse. So it's root 3 over 2. Yeah, very good. So root 3 over 2 is over here at pi over 3. Pi over 3, we're at root 3 over 2. And how about for pi over 6? Pi over 6, the value at sine is 1/2. 1/2. Okay, so those are, once you have these values, now you also know these values. You also know a couple of values over here. A lot of values get filled in from knowing sine of pi over 3 is root 3 over 2. Sine of pi over 6 is 1/2. You get similar things for cosine, right? There's a couple of places about sine and cosine that you can get out of a 30, 60, 90 triangle. What's the other triangle in trigonometry? 45, 45, 90. Okay, equilateral triangle, 45, 45, 90. 45 is pi over 4 radians is 45 degrees. This is supposed to be 45 degrees. 45 degrees, pi over 4 radians. And what is sine of pi over 4? Let's say the hypotenuse is 1, then these two side lengths are the same, and their squares must add up to the square of 1. So they must be root 2 over 2. Yeah. Or 1 over root 2, but you're taught for some reason you can't have radicals in the denominator, whatever. Root 2 over 2. So there's one more value of sine that we know, which is over here. Pi over 4 takes the value root 2 over 2. Okay, and the corresponding dots are along with it. These are the only values of sine, cosine, cosecant, tan that people reasonably evaluate. Although, what would sine of pi over 12 be? How would you work out sine of pi over 12? Say it again. Dividing by 3 is tricky, but dividing by 2, we have a half angle formula for sine. So if you wanted to work out sine of pi over 12, you know cosine of pi over 6. So you could work out what sine of pi over 12 would have to be from a half angle formula. Okay, so there's a bunch of you get lots more formulas, get others from half angle formulas. Okay, we have 10 minutes and we got to do exponential functions and logarithm functions. What's an exponential function? Like, what's the graph of y equals 2 to the x? When x is 0, 2 to the 0, 1. Okay, that's 1. 2 to the 1, 2, 2 to the 2, 4, 2 to the 3, 8. Okay, so we're getting big. How about 2 to the negative 1? A half. 2 to the negative 2, quarter, and so on, an eighth. Okay, so this is the graph of 2 to the x. What about the graph of 3 to the x? Same thing, yeah, it goes through 1. At 1, it goes to 3. At 2, it goes to 9. At 3, it goes to 27. At negative 1, it goes to a third and a ninth, and so on. So it's got this shape. And there's some magical number between 2 and 3. Whoops, go away. No. I don't know what that was. There's a magical number between 2 and 3 called E, which is like 2.7 something. And what's special about E? I don't know if you actually know this. What's special about E? Well, I'll give you the real definition of E. You probably learned some other definitions of E. There's a variety of ways of thinking about E. What's special about E is that the tangent line here has slope 1. It's exactly a 45-degree line. If you go on 3 to the x, the slope is a little bit bigger than 1. And if you go on the 2 to the x curve, the slope is a little bit less than 1. And somewhere in between, it's this magical number where the slope is exactly 1. That's E. Okay. We'll come back to that. What are the properties of E? Or what's the inverse function of E? Somebody mentioned replacing x and y. What's the inverse function of E? The natural log, right? So y equals the logarithm of x, which some people write ln. I'll always write log. If I don't specify the base, it's the natural base. Okay, this is log base E of x. It's the inverse function of e to the x.